Inside First Solar's panel factories, manufacturing is governed by a principle that separates industrial-scale solar from consumer technology. Energy production must be predictable, durable, and scalable over decades. These facilities are not optimized for visual spectacle or rapid iteration. They are optimized for long-term reliability under some of the harshest environmental conditions on Earth. First Solar's manufacturing philosophy begins with materials science. Unlike conventional crystalline silicon panels, First Solar's approach is built around thin-film semiconductor technology. This decision shapes everything that follows, from factory layout to automation strategy to quality control. The goal is not maximum wattage per cell in ideal conditions, but consistent energy output across heat, dust, and long operational lifetimes. Before physical production begins, every panel design exists as a fully simulated system. Semiconductor behavior, electrical performance, thermal stress, and degradation patterns are modeled together. These simulations define how production lines are configured, how process parameters are controlled, and how tolerances are enforced. Manufacturing becomes the execution of a validated physical model. The factory floor is designed for continuous, linear flow. Large sheets of glass enter the facility and move through a sequence of tightly controlled processes without interruption. Automation governs timing, alignment, and handling. Human intervention is minimized not for speed, but for consistency. Variability is the enemy of long-term performance. Assembly begins with glass preparation. Panels start as pristine glass substrates that are cleaned to optical standards. Any microscopic contamination can affect semiconductor adhesion and long-term output. Automated washing, drying, and inspection systems ensure uniformity before material deposition begins. Thin-film semiconductor layers are applied using vapor deposition processes inside sealed chambers. These environments are controlled precisely. Pressure, temperature, and material flow are regulated continuously. Inline sensors monitor layer thickness in real time, adjusting parameters instantly to maintain uniformity across the entire panel surface. Laser systems then segment the semiconductor layers into precise electrical cells. These cuts are measured in microns, but they determine how current flows across the panel for decades. Vision systems verify pattern accuracy immediately, preventing defects from moving downstream. Once electrical layers are complete, panels move into lamination. Protective glass and encapsulation materials are bonded under controlled pressure and temperature. This step seals the active layers from moisture, dust, and mechanical stress. Lamination quality is critical to long-term reliability, especially in extreme climates. Mechanical integration follows. Frames are installed using automated fastening systems that control torque precisely. Junction boxes are mounted and sealed to protect electrical connections. Each mechanical action is logged as part of the panel's digital identity. Throughout assembly, data collection is continuous. Every panel accumulates a digital passport containing process parameters, inspection results, and performance metrics. This traceability allows First Solar to link field performance back to specific manufacturing conditions years later. Quality control is not isolated to the end of the line. Inspection systems are embedded throughout production. Optical scanners, electrical probes, and imaging systems evaluate panels at multiple stages. Defects are detected early, when corrective action is still possible. Human expertise remains present, but in a supervisory role. Engineers monitor process stability, investigate anomalies, and refine parameters. Automation executes, humans decide. This balance ensures that production remains disciplined while still capable of improvement. Energy efficiency is built into the factory itself. Water recycling systems, energy recovery processes, and optimized equipment scheduling reduce the environmental footprint of production. The factory operates as a demonstration of the sustainability principles the panels are designed to support. By the time a panel reaches the end of assembly, it is not simply finished. It is fully characterized electrically, mechanically, and digitally. The factory knows how it was built, how it should perform, and how it will be supported throughout its life. But manufacturing precision alone does not guarantee trust. That trust is earned when panels are pushed beyond ideal conditions and proven under stress. If this look inside how First Solar builds its panels helped you understand the engineering behind large-scale solar power, make sure to like the video. Once assembly is complete, First Solar's panels enter the phase where performance claims are no longer theoretical. Inside First Solar's validation facilities, testing exists to answer one question only: will this panel deliver predictable energy output for decades under real environmental stress? Validation begins immediately at the line with electrical performance testing. Each panel is subjected to flash testing that simulates sunlight exposure, generating current voltage curves in milliseconds. These curves are compared against manufacturing benchmarks to verify power output, efficiency, and electrical consistency. Panels that fall outside defined limits are isolated before moving forward. Electroluminescence imaging follows. Under controlled excitation, panels emit faint light patterns that reveal microcracks, non-uniformities, or hidden defects within the semiconductor layers. These flaws may be invisible to the eye but can degrade performance over time. Automated imaging systems classify defects by severity, allowing corrective action or removal before deployment. Thermal validation is critical for thin-film technology. Panels are exposed to sustained heat loads while electrical performance is monitored continuously. Temperature coefficients are measured to confirm that output remains stable under high ambient temperatures, a key requirement for large-scale solar installations in desert and industrial environments. Environmental testing pushes panels far beyond typical operating conditions. Temperature cycling chambers simulate years of day-night expansion and contraction in compressed timeframes. Humidity exposure evaluates moisture resistance and seal integrity. Panels are stressed repeatedly to reveal any weakness that could emerge over long service lives. Mechanical durability testing evaluates resistance to physical stress. Panels undergo wind load simulations that flex frames and glass under controlled pressure. Impact testing replicates hail strikes and debris contact. These tests confirm that structural integrity is maintained without compromising electrical performance. Insulation and safety validation ensure panels meet stringent electrical safety standards. High voltage testing verifies insulation resistance, grounding integrity, and protection against leakage currents. These steps are essential for grid-connected installations where safety margins must remain intact for decades. Long-duration reliability testing extends validation over time. Panels operate continuously under load while performance metrics are tracked. Subtle degradation trends, such as output drift or contact resistance changes, are identified long before they could affect energy yield in the field. Quality certification is systematic and traceable. Each panel's test results are linked to its digital passport, creating a permanent record of compliance. This traceability allows First Solar to correlate field performance years later with specific manufacturing and validation conditions. Validation does not focus solely on individual panels. Batch-level analysis identifies patterns that individual tests may not reveal. Statistical monitoring ensures that production remains stable across high volumes, preventing systemic issues before they escalate. Human engineers remain central throughout testing. While automation executes validation at scale, engineers review anomalies, refine thresholds, and update test protocols. Accountability remains human, especially where long-term reliability is concerned. Only after panels demonstrate stability across all validation layers are they approved for shipment. But even the most rigorous testing cannot fully replicate the complexity of real-world deployment, where climate, dust, and grid conditions vary continuously. True validation continues after panels leave the factory and operate at scale. If you want to see how real-world data reshapes First Solar's manufacturing decisions, make sure to subscribe. When First Solar panels leave the factory, manufacturing does not end. It transitions into the environment that ultimately defines success: real-world operation at scale. For First Solar, deployment is not a handoff, it is an extension of engineering. Utility-scale solar farms, industrial installations, and grid-connected projects become living test environments that continuously inform how future panels are designed, built, and validated. Once installed, panels begin generating operational data under real sunlight, weather, and grid conditions. Power output, temperature response, degradation rates, and fault events are monitored over long periods. This data is collected across regions with extreme heat, dust exposure, humidity, and seasonal variation, conditions impossible to fully reproduce in laboratories. Digital performance models evolve using this field data. Assumptions made during design and testing are validated or corrected. If panels exhibit superior stability in high-temperature environments, manufacturing parameters are reinforced. If unexpected degradation patterns appear under specific conditions, material formulations and process controls are refined. Thin film technology benefits especially from this feedback loop. Real-world temperature coefficients, low-light performance, and long-term stability profiles directly influence next-generation panel design. Manufacturing recipes are adjusted not based on short-term efficiency gains, but on sustained energy yield over decades. Predictive analytics transform reliability management. Subtle indicators, minute changes in output curves, temperature sensitivity shifts, or electrical resistance are detected early. These signals allow operators to schedule maintenance proactively while enabling First Solar engineers to adjust future production tolerances before issues propagate. Software plays an increasingly important role. Performance monitoring platforms analyze fleet-level data across thousands of installations. Insights derived from these platforms feed directly into factory control systems, refining deposition parameters, lamination strategies, and quality thresholds. Manufacturing evolves in response. Test protocols are updated to reflect real operating profiles rather than theoretical extremes. Environmental stress tests are recalibrated based on observed field behavior. Quality metrics become more precise with each deployment cycle. Scale amplifies learning. First Solar's panels operate across continents, climates, and grid architectures. This diversity reveals patterns that isolated projects cannot. Global data aggregation allows the company to identify systemic risks early and deploy improvements across all factories simultaneously. Sustainability remains central throughout evolution. Real lifecycle data informs material selection, recycling strategies, and energy consumption targets. Manufacturing processes are refined to reduce water use, energy intensity, and material waste. The factory itself evolves alongside the product it produces. Human expertise remains critical. While AI systems analyze massive datasets, engineers interpret results, validate conclusions, and make design decisions. Transparency is enforced, especially where automated insights affect long-term reliability and environmental impact. Future First Solar factories are designed around this closed-loop model. Design, manufacturing, validation, deployment, and optimization form a continuous system. Simulation accuracy improves as real-world data refines assumptions. Production becomes more resilient with every generation. Innovation becomes cumulative. No panel exists in isolation. Each deployed unit contributes intelligence that shapes future architectures, process controls, and manufacturing discipline. Progress is driven by evidence, not speculation. In this model, solar manufacturing is not a linear process. It is a living system that learns continuously. From factory floors to vast solar farms, First Solar's approach demonstrates how clean energy infrastructure earns trust, through systems that prove themselves over time, at scale, and under real conditions. If this inside look at how First Solar builds and evolves its solar panels changed how you see the engineering behind clean energy, leave a comment with your thoughts.